So now we're going to learn a direct comparison test. All right. And so if we read this, if A is greater than or equal to 0 and B is greater than or equal to 0, which means we have positive things going on, the summation of B converges if A is between 0 and B, then A also converges. This is the way I want you to think of it. It always says what? In this case, it says B is greater than A. Does everybody see that? So if I use B as red and then A is, let's say, green, A is less than B. Does everybody see how that worked? All right. And if B converges, then A also converges because it kind of gets squeezed underneath. Do we see how that worked? All right, and the way that I want you to think of it is I want you to think of bigger converges, the smaller one will as well. So I designated that as BC. All right, and hopefully you can remember that part because we are in what? BC. If the bigger converges, the smaller one will do the same. All right, and then if the smaller one diverges, so here I still have A is less than B. If the smaller one diverges, then the bigger one, guess what, also diverges. And so the way that I want you to think of that one is SD. All right, so smaller BC, SD. Does it say anything about like bigger diverges? Does it say anything like that? No, we won't know anything then. Does it say anything like smaller one converges? Do we know anything about the bigger one? No. All right, so it has to go in this order. But if you think about it, if your smaller one diverges, this one will also not go to 0 quick enough. All right, and then if this one goes to 0 quick enough, the smaller one will also converge because it has to be underneath it. All right, it has to go quick enough. All right, so here we go. This is the way we do it. All right, so let's look at this example. So I have n cubed over n cubed plus 1. What should we always use first? The nth. All right, so if I take a limit to infinity, does this thing go to 0? No. So what do we say? It diverges, why? By nth. Because does it go to 0? No, it goes to a number. It doesn't go to 0, so it already diverges. All right, let's look at part B. So now I have 1 over n cubed plus 1. If I do a limit to infinity, does it pass the nth? Yes. So we have to do something else. This is the way I want you to think of it. All right, this is going to be kind of hard. I put my little fat thumb over everything except for the higher thing. So on this one, I put my fat thumb over everything but the 1 over n cubed. All right, and so I tried to do that for you people that are on the other thing. So just kind of put your thumb over that other part. So that's what you're going to compare it to. All right, so you're going to compare to the summation of 1 over n cubed. And what do you know 1 over n cubed does? That converges. Why does that one converge? That one converges by p series. All right, and so now we need an inequality. So now we have 1 over n cubed, and we have 1 over n cubed plus 3, or plus 1, I'm sorry. So which one is bigger? 1 over n cubed is bigger. It's always going to be bigger than or equal to. And so what you know is that what? The bigger one did what? Converge. So the bigger one converged. What do we know the smaller one must do? Converge. So this one converges. Why? By direct comparison test. All right, DCT. You don't actually have to put the little dots. You can just say DCT. All right. All right, cool. Let's look at part C. So again, use your flick fat thumb. The books should honestly say this. All right, I'm going to try to copyright it. All right, so what should we compare it to? 1 over 3 to the n. So we compare it to 1 over 3 to the n. So a summation of 1 over 3 to the n. Now, what does this one do? 0. Okay, sure. It passes the nth. Yes, it does. All right. So what do we compare? So what do we know this one does? Does this converge or diverge? It converges. Why does it converge? No. Why does it converge? What test? By GST. All right? And so this is really 1/3 to the power of n. Yes? All right? And so my ratio is 1/3, which is less than 1, so it converges by GST. Now we need to figure out which one's bigger. So now we have 1/3 to the n plus 2, and we also have 1/3 to the n. So which one is bigger? The 1/3 to the n is bigger every single time, because this one grows faster on the bottom. 3 to the n plus 2 grows faster on the bottom, which makes this fraction smaller. Does everybody see this? All right, and so this one's going to be bigger. All right, so what do you know? The bigger one converged again. All right, and so the bigger one converged, which means this smaller one also does what? Converges. Now, what do we say? It converges how? By DCT. All right. All right, so on this one, I now have 1/√n minus 1. So what do we need to do? Compare it. All right, so what do I compare it to? 1/√n. So I'm comparing to my summation of 1/√n. And what do I know that thing does? That one diverges by p series. Why does it diverge? Exactly. All right, because that has a power of 1/2. So that one diverges by p series. Now we need to write our inequality. So now we have 1/√n, and I have 1/√n minus 1. Well, which one is bigger? The one that the square root n minus 1 is the bigger one. All right, because this one actually has a smaller denominator now, because I'm subtracting from it, which means it's what? It means it's bigger. So, guess what happened? What do I know about this smaller one? It diverged. So what do I know about my bigger one? It also diverges. So this one diverges why? By DCT. All right, pretty good.
And where it says in the...
This next one, I have cosine n over 2 to the n. My flicks fat thumb doesn't work exactly here. All right. However, you should know something about cosine. What does cosine always go in between? 1 and -1. And so what should you compare it to? What do you think you would compare it to? 1/2 the n. All right, exactly. So we're going to compare this to something we know. And so we're going to compare it to 1/2 to the n, because we know that one. Does everybody see why we compared it there? All right, and so if we know that one, what does this one do? It converges. Why? By GST. All right, and now I need to write my inequality statement. So now I have 1/2 to the n, and I have cosine n over 2 to the n. Now, you kind of already thought about this one, because cosine goes in between what? -1 and 1. So which one is always going to be bigger than or equal to? The 1/, because the cosine could also be negative. Is everybody following me? Or less than 1. All right. And so my bigger one does what? My bigger one converges. So we're still good, aren't we, Cole? Yeah. All right. So what do we know about our original thingy? That converges. Why? By DCT. All right, we got lots of gang signs now. We got 6 so far. We're going to get 7 today. All right, let's look at this next one. All right, flicks fat thumb, what do we compare it to? All right, so we're going to compare it to 1/n⁴. And what do we know 1/n⁴ summation does? It converges. Why does it converge? By p series. All right, so now we're going to find out which one's bigger by our inequality. So now we have 1/n⁴, and we have 1/n⁴ minus 10. Which one's bigger? The minus 10 one. Well, this one, the smaller one, does what? Smaller one converges. Do I have something for that?
Gosh darn it.
So what do we need? Another test. All right, let's do the other one. All right, sometimes the inequalities needed won't hold. All right, and so we need to use another test. And this is my favorite test, honestly, and it should probably be yours afterwards. This one is called the limit comparison test. All right, and so all we need is that they're positive, and our limits become finite. And what I mean by our limits is we put one on top of the other, and we get a number. So I take a limit to infinity, one on top of the other one, and I get a number. Now, if you use Flick's fat thumb, the number will be 1 every single time. All right, if you look in any textbooks, they will not get 1. I'll show you what I mean with some examples on the next page. All right, so it will take whatever you compare it to. So for instance, if you compare it to something that diverges and you pop out a number by our limit comparison test, guess what the other one does? Diverges. And the same thing, if you compare it to what it converges and you pop out a number on our limit to infinity of your fraction, guess what it is? It converges. All right, so put it into practice. Here we go. So now I have 1 over 3n squared minus 4n plus 5. All right, so use Flick's fat thumb. What are we going to compare it to? 1 over 3n squared. Love it. All right, so we're going to compare it to 1 over 3n squared. Well, what do you know that does? That converges. Tell me why. By p series. Oh, that was good, Nick. You have a future. I like it. All right. So that one converges by p series. I'm going to show you all the way out on this one, but soon I'll just flip my fraction. So we're going to take a limit to infinity of 1 over 3n squared minus 4n plus 5 over 1 over 3n squared. Now, I want to, actually, I'm pausing. The reason why we don't want to use DCT on this one is that, like, it's really hard to figure out which one's bigger or smaller, okay? Because I now have 2 terms that I'm dealing with plus a variable, okay? And so direct comparison is going to be really difficult to show because I have so many terms and variables going on. Does that make sense? All right, and so that kind of leads us into this other guy. Now, when I divide by a fraction, I'm really multiplying by what? A reciprocal. So I actually won't do this step ever again. Okay, what are we going to do? We're going to multiply by its what? Its reciprocal. So this is really a limit as n approaches infinity of 1 over 3n squared minus 4n plus 5, and then times 3n squared over 1. I will jump there every single time. All right. However, if they give an example of in a text, they will make the fraction. Is everybody hearing me? Okay. So it technically is a fraction, but I'm going to multiply by its reciprocal right away. All right. And so when I take a limit to infinity, what do I get? 1 every single time. All right. Textbooks and college professors, they would actually compare to 1 over n squared. Okay, they wouldn't add the 3 on it. I like to just keep it because every single time I take a limit to infinity, guess what we're going to get? We're going to get 1. Okay, so professors will make you think a little bit harder. They won't put the 3 on there, and so then they'd get a 1/3, which is still finite and positive. Is everybody following me? All right, and so it's still good. However, I don't want to think that hard. All right, so we got a number, so guess what we know? This converges by LCT. All right, pretty cool. All right, let's look at this next one. All right, so use Flick's fat thumb. What do we compare this guy to? No. All right, so if you're going to cover it up, you're going to cover up all of that, right? So you'd have n to the 4th over 4n to the 5th. Does everybody follow me on this? And so really, what are we comparing it to? 1 over 4n. All right? A textbook or a college professor will compare it to 1 over n. Just throwing that how they'll do it. All right? I like to do it this way. All right? So what do we know 1 over 4 to the n does? Or 4n, I should say. I'm sorry. What do we know that one does? That one diverges. This one's actually special. This one diverges why? By p series or harmonic. I like to give it its name when it's necessary. You can say p series. However, it is a diverging because it's a harmonic series. All right, which is a special case for a p. What's up?
Oh, just keep making.
Gotcha. All right. So now we're going to take a limit. So do you see why we don't want to use direct comparison again? Because I got a lot of crap going on to figure out, and I don't want to think that hard. All right. So now I have a limit as n approaches infinity of n to the fourth plus 10 over 4 to the n to the fifth minus n cubed plus 7 times 4n over 1. So what do we know happens? It goes to 1. I don't have to think at all because I use my flick fat thumb. So what do we know? The original does what? Diverges because why? By LCT. All right. All right, so what are we going to compare this one to? 1 over n cubed. First of all, does it pass the nth? Yes. All right, so we need another test. All right, so we're going to compare it to 1 over n cubed, which does what? Converges, why? By a p series. So now we're going to take a limit as n approaches infinity of 1 over n cubed minus 2 times n cubed over 1. And what do we get? 1 every single time. All right, so what do we know? Converges by LCT. All right, pretty good. All right, let's look at this next one. All right, so does it pass the nth? Yeah. So what are we going to compare it to? 1 over square root 3n. All right, so we're going to compare it to 1 over square root 3n. So what do we know it does? Diverges. All right. Again, on the textbook, it would just compare it to 1 over square root n. Okay. I think you just keep constant multiple. All right, so it diverges why? By p series. All right, it diverges by p series. All right, and so now we're going to take a limit as n approaches infinity of 1 over square root 3n minus 2 times square root 3n over 1. And what do we know it's going to do? Goes to 1. All right. You like my fat thumb, don't you? All right. And so what do we know? Diverges why? By LCT. All right. Pretty good. All right. Let's quickly read. All right. So we're going to do day 2 of your homework packet. But find something that you know to compare it to. All right, usually your fat thumb can get rid of it to figure out what you compare it to. All right, and then either the bigger one converges, you have to show your inequality for DCT, or your smaller one diverges and it will take its place. All right, and then a lot of the times LCT gets away with it. So then whatever you compare it to, take a limit to infinity, you'll probably get 1 if you use your thumb right. All right, and if you get a number, it takes the place of what you compared it to. All right, pretty good? All right.